Good morning, good afternoon, good evening. Hello, welcome to chapter 15. Today we're going to talk about digital elevation models. I'll try and make this fairly quick just to sort of give you an introduction to some of the concepts that we're going to be introduced in this chapter. So the first thing that we're dealing with here is we're going to learn a new datum. How exciting is that? The vertical datum. In all of the work we've done so far, we've been working with the geographic coordinate system with points of latitude and longitude, also expressed as x and y, and the different ways to project and calculate them. But now we're going to add that z value, that vertical up and down value, also known as the z-axis. So there is actually a vertical datum. It is called the North American Vertical Datum of 1988, and there's also one done in 1929. And what a vertical datum is, what that means is a height relative to a defined surface, and the defined surface is the mean sea level of the geoid. So if you go back to your GIST class, if you took one, you remember that geoid is the sort of hypothetical, theoretical shape of the Earth in all of its lumpy imperfection, and the ellipsoid is what we get when we sort of average it out and smooth it out. So how we get our vertical datum is by measuring off the height of that geoid depending on where you're at. And by doing this, we can create a sort of representation of the actual topography of the area that we're looking at. So when we're doing this in GIS, and in this chapter, we're doing terrain surface analysis, or a digital terrain model. This is also known generally as pseudo 3D or 2.5 3D because it's not actual 3D, which we'll actually get to in a couple of chapters, but it's more representing it in a two-dimensional screen image. So a digital elevation model is based upon, as we discussed, that vertical datum. It looks like this. I guess I can use my cursor here. This black and white kind of fractal-like image. And much like when we're looking at rasters, when they're first taken through a satellite image, you get sort of panchromatic image where sort of the lighter colors might represent something that's of a certain value or height, and the darker values represent something low. That's what's happening here. So this isn't necessarily photographed, but it has that same kind of representative scale from dark to light. So when you load it into your table of contents on ArcMap, the image is going to look like this, and in your table of contents, you're going to get this. And this sort of represents the different elevations, different elevation classifications that exist on your DEM that you have, DEM file in there. So just a little bit more on these DEMs, DEM people. The National Elevation Database is what it's based on, although it was replaced into the 3D elevation program, all run by the USGS. You can get it from the national map in ArcGIS Online. You can also, which means you can also download it into your ArcMap if you're working online, if you're on your desktop ArcMap, and you can bring the information in from ArcGIS Online. The current resolution is 30 meters, or 1 arcsecond. We'll get into a little bit more about what that means in a few slides. But you can get resolution as fine as 1 meter or 1/9 arcsecond for certain locations. Most of that information is actually, you have to pay for it, and it's only for certain parts of the country. And again, this is based on the National Vertical Datum of 88 and NAT 83. And we also get this information from several different satellites. The two main ones are Aster on Terra and the Shuttle Radar Topography mission. So let's talk about an arcsecond for a second. You'll see this come up increasingly in the book as he talks about the kind of data you're looking at. And you'll start seeing it more and more when you're digging around in GIS data. And what it means is another way of talking about the spatial resolution of the document or the file you're looking at. So for all intents and purposes, you know we're looking at a sphere. A sphere is a circle. It can be put into 360 degrees as we see down here. And those 360 degrees are divided into 21,600 minutes, and those minutes are divided into 1,296,000 seconds. So our 30-meter resolution is equal to 1 second of that whole span there. And what that means is, of course, if you took all those seconds and added them up, you'd go around the whole Earth if you just did them in a straight line. I think sometimes it's easier to think about this in terms of these big numbers, but it's easier to think about it in terms of small numbers. So if we think about the 30-meter resolution as representing 1 second, if you want to look at a third arc second is 1/3 of 30 meters, which is 10 meters. So that will give you 10-meter resolution. Again, you'll probably see 1/3 arc second. That's fairly common for a higher resolution. So if that doesn't thoroughly confuse you, then you can take a look at this nice equation down here at the bottom, which will, I'm sure, help bring it all to life. It's actually not a difficult concept once you think about it a little bit, and it's good to sort of familiarize yourself with it just before we kind of head into all of this. So when we're looking at digital terrain modeling, there are a number of things we can do. We can drape, so we can take a satellite image and actually drape it over the model and create that pseudo 3D we were talking about a moment ago. We can do hillshade. Hillshade is really interesting. It's basically imitating the angle of the sun to create a better visual cue about what the landscape looks like. Slope and slope aspect, that lets us know how steep and how flat or level various sides of the topography are. Viewshed can let us know how and what we can actually see from one point to another, which is also similar to line of sight. A little later down the line, we'll learn about triangulated irregular networks and contours as well, which is part of digital terrain modeling. So the sun and draping, I just spoke about this a moment ago, but this gives you another idea of what we're talking about. So here we have our DEM on the left, and on the right we have hillshade with the sun at an elevation of 45 degrees and an azimuth of 315 degrees. And that lets us know that that is what that landscape looks like when the sun is hitting it that way. And down here we see a Landsat image draped over a DEM. And this DEM has actually been extruded a bit to give it more effect. But you can see you've taken the actual imagery in a normal color spectrum and draped over that to give it a more pseudo 3D effect. So if you wanted to create your own hillshade, anytime you bring a DEM into ArcMap, it's very simple to actually take a look at it in any kind of hillshade you want. So you go to Data Frame, Properties, and Illumination, and you can play around with it and just look at what the sun looks like at different times of day. Okay, so on to slope and slope aspect. So a DEM only tells us part of the story of the landscape. To get a fuller picture, determining the slope or the rate of elevation change at a given location gets closer to creating a more accurate model. Part of determining slope is also finding the aspect, which tells us which direction the steepest slope at a location is facing. These are produced using a few different geoprocessing tools, and it will actually create a new raster output layer. So here's a little information on how slope is determined. But let's talk quickly about aspect because it relates to the raster discussion we sort of came out of in the last chapter. In order to find aspect, actually, those rasters have to talk to each other. So those friendly rasters I discussed are doing 8-way or 4-way communication with the rasters around it to determine and generalize what the direction will be. When you do your lab, you'll come across the aspect and you'll find that it actually determines all the different aspects that you can possibly find in there. I think that's 8 of them. So it's very interesting to see, and actually turns out a very colorful map, as you'll find out. And this is what we see here. So you can see this is the slope that's been determined, so we can see how steep everything is versus how flat, so the red to the green. And over here we have the slope aspect. So based on the color you see here, it's north, northeast, east, southeast, etc., etc. So let's talk quickly about visibility analysis. Viewshed is a really cool tool. It basically will show you essentially what you can see from a given point. So in this case, the point we're looking from is the tip of the fan, and what we're looking out at, what we can see is the sort of visible parts, and the red is stuff we can't see. And then down here we see the line of sight analysis, again looking from point A to point B on this picture here on the upper right, the green is what actually can be seen versus the red is what is blocked. And this is different graphical representation of how that is viewed. So preparing for the lab, you'll be using 3D Analyst. It's an extension. Remember, you'll have to turn it on. You'll start working with histograms, which is an interesting tool to learn how to get comfortable with. And not all raster data will have an attribute table, but you can make one. So I think you get to experiment with that a little bit. All right, I hope you guys enjoy the lab, and we'll see you next time. With slope and slope aspect is we have to get the rise and run of the elevation and the horizontal aspect in order to get a fuller picture of what is going on in the model. So part of determining slope is also finding aspect.